All right, welcome everyone to the deep dive. You guys are here because you want to learn a ton of cool stuff super quickly, right?
That's right, without it feeling like an information overload. And we're here to deliver exactly that.
We got some really interesting material to go through today. We're going to be looking at what makes buildings strong and safe.
Hmm. More specifically, we'll be going deep on rebar,
There you are, yep.
that steel reinforcement that's hidden inside concrete. You might not see it, but it's what gives the concrete its strength. It's truly doing the heavy lifting.
For sure. We've got some great resources today. We're going to look at the basics of how houses are built, and we'll also explore the fascinating history of rebar, how it has evolved over time, and what makes it so important.
Absolutely. Our mission is to extract the really key insights from these materials. We'll be talking about different types of house construction, the crucial role of rebar, and how we can be certain that the rebar being used is top quality.
Okay, so let's jump right in.
So your sources start off by describing the three basic ways people build houses: mud, brick, and concrete. It's a good place to start because it shows just how different the durability of building can be depending on what it's made of.
Right. They talk about mud houses, which are considered um, uh, less durable, not the strongest, but a big plus is that they're environmentally friendly.
Mm-hmm.
Then we had brick houses, which offer a bit more strength, but they're still not as durable
As
as
concrete.
yeah.
Exactly. Concrete houses are the top tier when it comes to durability and strength. And they also have something called high ductility, which we'll get to in a bit. Important. But it's worth noting that concrete, while being super strong and long-lasting,
Yeah,
making it does have an environmental impact. It's something to consider.
absolutely. And one of the sources talks about the 2001 Bhuj earthquake in India to really highlight why it's so important to have strong buildings.
Right.
This was a 7.7 magnitude earthquake that sadly resulted in around 20,000 deaths. And it all happened in just 82 seconds. Another 150,000 people were injured. This event just shows how critical it is to have well-built structures, especially in areas prone to earthquakes or other natural disasters, because those strong structures can really save lives.
Absolutely. The source uses the term failure modes when discussing this earthquake.
Right, it refers to the specific ways structures can fail during an earthquake. So what are some of these weaknesses, failure modes, that they observed in Bhuj? And how could better materials and construction techniques prevent them?
Well, in earthquakes like the one in Bhuj, a lot of the older buildings just couldn't cope with the intense shaking and stress. You'd see walls collapsing, foundations shifting, entire buildings just crumbling because they weren't designed to handle that kind of movement.
Right.
This is where the evolution of building materials, and especially rebar, becomes super important. And speaking of that evolution, your sources have a really interesting timeline showing how rebar has improved over the years.
It's a pretty amazing timeline. It starts way back in 1867 with what are called mild steel bars. And those had a yield strength of about 250 megapascals,
Right.
or MPa. Then around the beginning of the 20th century, we see the introduction of cold, twisted, deformed bars, which had a yield strength of 415 MPa. And by the 1960s, those were becoming quite popular.
Mm-hmm.
But then things get really interesting around 1980.
Yes. That's when we see the introduction of thermomechanically treated bars, or TMT bars.
BMT, okay.
And these bars, while they really changed the game, they have a range of yield strengths from 415 all the way up to 600 MPa. And the most recent development, which is really impressive, is the IS.1786 Fe550D Tiscon 550SD. This is specifically classified as spec high-strength superductile.
Super ductile. So what does that mean?
Ductility refers to a material's ability to deform, to bend and stretch under stress without breaking. Think of it like a piece of taffy. You can pull and stretch taffy without it snapping. That's because it's ductile.
Okay, makes sense.
A brittle material, on the other hand, like a cracker, will just break if you try to bend it. It has low ductility.
Gotcha.
So superductile rebar is designed to withstand a lot of deformation without breaking. This is super important, especially in earthquake-prone areas, because it allows a building to move with the ground shaking instead of just collapsing.
So it can kind of like absorb the shock.
Exactly.
Okay. You mentioned a table that compares mild steel bars to this Tiscon 550 SD, and it really shows how much rebar technology has advanced.
It really does. So if you look at the chemical composition, some of the limits might seem similar at first glance.
Right. The table says the maximum percentage of carbon is 0.25% for both mild steel and Tiscon 550 SD.
Yep, that's right. And the carbon equivalent is also capped at 0.61% for both.
So what is this carbon equivalent thing, and why is it important?
It's basically a way to estimate how hard the steel will be and how easy it is to weld. Keeping it below a certain level helps ensure that the rebar is not too brittle and can be easily welded during construction.
Okay, but if you look closer at the table,
Exactly. There are some important differences.
the maximum percentages of sulfur and phosphorus are lower in the Tiscon 550 SD at 0.035% compared to 0.040% in mild steel. And the combined maximum for those two elements is also lower in the Tiscon 550 SD.
Right.
So why are those tiny differences important?
Well, those impurities can make the steel brittle and more likely to crack under stress. By controlling them really tightly, you're basically getting rid of tiny flaws that could potentially cause big problems down the line.
Okay.
And then there are the elements that are specifically added to improve the rebar's performance. For example, the Tiscon 550 SD has a higher percentage of manganese compared to mild steel, 1.8% versus 1.4%. And it also contains silicon at 0.3%, which is not even specified for mild steel. What do you think those extra elements are doing?
Well, I know manganese is often added to steel to increase its strength and hardness.
Exactly.
And silicon is sometimes used to improve corrosion resistance and can also boost strength.
Spot on. Now let's get to the really exciting part, the strength numbers. The minimum yield strength for the Tiscon 550 SD is a massive 570 MPa compared to just 250 MPa for mild steel. That's more than double.
Wow.
And the ultimate tensile strength is also significantly higher, 660 MPa for the Tiscon 550 SD versus 410 MPa for mild steel.
Okay, so that basically tells us how much stress a rebar can withstand before it either permanently bends or completely breaks.
Exactly. But remember, it's not just about pure strength. Ductility is super important too. And the Tiscon 550 SD has a minimum uniform elongation of 5%, while mild steel doesn't even have a specified value for that. And when we look at total elongation, the difference is even more striking. The Tiscon 550 SD has a minimum of 16%, while, again, there's no value specified for mild steel.
So the Tiscon 550 SD can stretch a lot more before it breaks.
Precisely. And to quantify that reserve strength, how much stress it can handle beyond its yield point before actually breaking, we look at the ratio of ultimate tensile strength to yield strength. For the Tiscon 550 SD, that ratio is at least 1.15, meaning it has a significant safety margin.
Okay, so we've come a long way from that basic mild steel rebar to these high-tech, super ductile bars that are much stronger and can handle a lot more stress.
Exactly. And your source gives us a really helpful framework for assessing rebar quality. They call it the 5 pillars to assess rebar quality.
Okay, so what are these 5 pillars?
The first pillar is load-bearing capacity. This is basically the yield strength. For the Tiscon 550 SD, that needs to be greater than 570 MPa. You'll often see markings on high-quality rebar, things like TA at Tiscon 550 SD, or DIN AR YREBAR.
Like stamps of approval.
Exactly.
Okay, what's the second pillar?
The second pillar is reserve strength. That's that UTS to YS ratio we talked about earlier. For the Tiscon 550 SD, it has to be greater than 1.5, and again, you might see markings on the bar indicating this. This means the rebar can handle even more stress beyond its yield point before it actually breaks.
Okay, makes sense. What about the third pillar?
The third pillar is appropriate ductility, which is all about that percentage elongation. The Tiscon 550 SD boasts superductility with at least 16% elongation. There's a great visual in the source that shows a 1,000 millimeter piece of non-ductile rebar next to a 1,160 millimeter piece of ductile rebar after they've both been stretched.
So the ductile bar stretched an extra 160 millimeters.
Exactly. That's a huge difference. The fourth pillar is pretty straightforward. It's just correct weight.
Okay.
The source doesn't give us specific numbers here, but it basically means that the rebar needs to weigh what it's supposed to for its given diameter and length. If it's too light, it might not have enough steel to provide the required reinforcement.
And a fifth pillar.
The fifth pillar is right chemical composition. This is all about controlling those impurities we talked about earlier, particularly sulfur and phosphorus. The sulfur content in the Tiscon 550 SD is kept below 0.035%, which helps to prevent brittleness and surface flaws. The same goes for phosphorus, which is also kept below 0.035% to prevent brittleness, especially at low temperatures. And they also carefully control the carbon content, keeping it below 0.25%. This ensures a good balance between strength and weldability and prevents the rebar from becoming too brittle overall.
It's amazing how much goes into making sure that rebar is high quality. And your sources also provide a pretty detailed look at the actual manufacturing process from raw iron ore to the finished bars.
It's quite a journey. It all starts with primary steel making, where the iron ore is converted into something called hot metal, most likely in a blast furnace, although the source doesn't go into detail about that specific step.
Right.
But then comes secondary steelmaking, where the hot metal is further refined and eventually turned into billets. Billets are basically like long, square-shaped pieces of semi-finished steel that will later be rolled into the actual rebar.
Okay. So what happens in secondary steelmaking?
First, the hot metal is transferred to an LD converter.
An LD converter. Okay. What happens there?
It's a special type of furnace where they can further refine the molten steel.
Okay.
And the first step in the LD converter is desulfurization. They inject something called Kamano reagent into the molten metal, which helps to remove excess sulfur.
Right, because too much sulfur makes the steel brittle.
Exactly. After that, they remove other impurities like carbon, manganese, phosphorus, and silicon. This is done by blowing high-purity oxygen into the molten metal from the top and stirring it with inert gas from below. And this happens at super high temperatures like 1600 to 1700 degrees Celsius.
Wow, that's hot.
Extremely hot. Then they add ferrule alloys to the molten steel in something called a ladle furnace.
What are ferroalloys and why are they added?
Ferroalloys are basically alloys of iron with other elements, like manganese, silicon, or chromium.
Okay.
They're added to adjust the final chemical composition of the steel and to give it the desired properties. And they also help to make sure the molten steel is homogeneous, meaning it's all mixed evenly. After that, there's a reheating homogenization step where the molten steel is further heated using graphite electrodes to ensure a uniform temperature throughout.
Okay, so now they've got this really pure, homogeneous molten steel. What happens next?
That molten steel is then continuously cast into billets. These billets are 12 meters long and 150 millimeters by 150 millimeters square.
Okay.
They're still incredibly hot, around 1700 degrees Celsius, and they're stored in something called the billet stockyard, ready for the next stage of the process.
Which is the rolling plant. So the billet gets moved from the stockyard to the reheating furnace, which the source tells us is a Brickmont reheating furnace using a gandola and an electro-hydraulic cross pusher.
That's right.
Sounds pretty high-tech.
It is. This furnace is a beast. It can heat 150 tons of steel per hour, and it can hold 85 billets at a time. It uses a walking beam mechanism to move the billets through the furnace, and they're reheated to up to 1100 degrees Celsius in something called the soaking zone. And to make absolutely sure the temperature is spot on, they use a pyrometer, which is a device that measures temperature from a distance.
Wow.
From there, the billet goes through the roughing mill, which has 4 horizontal stands.
So what do these stands do?
The stands are basically sets of heavy-duty rollers that squeeze the hot billet and start to shape it.
Okay.
The roughing mill reduces the billet size to 130 millimeters by 130 millimeters, and it also stretches it out to a length of 9 meters.
Okay.
And then it passes through something called pinch rolls.
Pinch rolls. What are those for?
Those help to guide the steel as it moves through the mill, making sure it stays on track. And then there are rotary shears, which are basically cutting wheels that can trim the ends of the billet or even cut it into shorter sections. There's also a pneumatic emergency shear for safety in case something goes wrong.
Okay. Makes sense. What happens after the roughing mill?
The billet then goes through an interfinishing stand and then a finishing stand. These further refine the shape and bring the billet closer to the dimensions of the final rebar.
Okay, and then comes the magic, right?
Yes, the part where that super ductility is achieved.
Right.
This happens in the water box, where the rebar goes through thermomechanical treatment, or TMT.
So what happens in the water box?
The red-hot rebar is rapidly cooled with high-pressure water. This sudden cooling drops the surface temperature from around 1,000 degrees Celsius down to about 200 degrees Celsius very quickly.
Okay.
This rapid cooling creates a hard, strong structure called martensite on the outer layer of the rebar.
Okay, I've heard of martensite. It's a very hard type of steel, right?
Exactly. But if the entire rebar were martensite, it would actually be too brittle.
Ah, so that's where the thermomechanical part comes in.
You got it. As the rebar moves out of the water box, the heat from the still hot core starts to diffuse outwards. This causes the temperature of that martensite layer to rise again to around 550 to 600 degrees Celsius.
So it's kind of like a self-tempering process.
Exactly. This tempering makes the martensite less brittle. And at the same time, the heat also transforms the inner core of the rebar into a more ductile microstructure composed of ferrite and perlite. So you end up with a rebar that has a hard, strong outer shell and a tough, flexible inner core. The perfect combination.
It's really clever.
It is. After the water box, the rebar is cooled down further on a rake-type cooling bed.
Okay.
And then it's cut to the final lengths using cold shears. These shears can cut rebar with diameters ranging from 6 millimeters to 40 millimeters, depending on the application.
Okay.
And finally, the rebar is weighed, tagged, bundled, and then loaded for shipping using an EOT crane, which is basically a big overhead crane.
And of course, there's a final inspection to make sure everything meets the required standards.
Absolutely. The source even mentions something called the ring test.
Oh, right.
They conduct these tests in the field to make sure that the rebar actually performs as expected in real-world conditions. They have examples of both failure cases and past cases, which really highlights the importance of ongoing quality control.
So it's not just about making the rebar correctly in the factory. It's also about making sure that it performs as expected once it's actually being used in a building.
Exactly. It's all about safety and reliability.
Okay, so to summarize, we've gone from these basic building materials like mud and brick to the sophisticated world of reinforced concrete. And we've seen how rebar has evolved from relatively simple, mild steel bars to these high-tech, super ductile bars like the Tiscon 550 SD.
Right. And we've learned about the 5 key pillars of rebar quality: load-bearing capacity, reserve strength, appropriate ductility, correct weight, and the right chemical composition. And we've also explored the intricate manufacturing process, from iron ore to the finished rebar. It's a complex process that involves a lot of science and engineering to ensure that the rebar is strong, durable, and safe for use in construction.
Yeah, it really is amazing when you think about all the steps involved in making something that we often don't even see, but that plays such a vital role in our built environment.
Exactly. It really makes you appreciate the engineering and the technology that go into creating the structures we rely on every day.
For sure. And it makes you think, with all these advancements in rebar technology and with the growing concern about the environmental impact of different building materials, what does the future of construction look like? How can we build structures that are both sustainable and incredibly strong and resilient?
Yeah, that's a great question. And I think it's something that architects, engineers, and material scientists are all grappling with right now. It's an exciting time to be in the world of building and construction, that's for sure.
Absolutely.
It'll be interesting to see what innovations emerge in the coming years.
For sure. All right. Well, on that note, we'll wrap things up here. Thanks for joining us on the deep dive. We hope you found this as fascinating as we did.
And we encourage you to keep exploring, keep learning, and keep asking questions.
We'll see you next time.